Right.
But then you multiply it by 2
But obviously, you know what this is.
Like here,
Yeah.
and do this.
Welcome back. We're gonna. Welcome back. Yes, absolutely. Off, left, right. Is that okay? Great. Okay. Oh, the screen. I thought I put that down. There we go. Much better. Okay, thank you. I need you guys. I look at the monitor back there. It doesn't tell me exactly everything. Okay, welcome back. I'll remind you that our exam is coming up a week from Monday, April 14th. It'll be on AM and the beginning of FM. However, today we'll very likely finish our discussion of FM. We'll get to the bottom of that. And we might even start a little bit on pulse code modulation today. But mostly that'll be next week. So, without further ado, Lecture 18, I think that's the number of this. FM demodulation, sort of the very end of FM is what happens when the FM signal wanders its way into the receiver. How do I pull back out the message signal? I'll remind you that on the building side we have the Armstrong method to generate FM, and while there are other methodologies, that is a good and solid way to do this. So we're going to look at what happens at the back end of it.
I think it might be 17.
It might be what?
17?
Lecture 17?
No?
No? Well, close enough. It's some integer number in the high teens, and
Sorry.
I'll double check that for next time.
Yeah.
So.
It's not that important.
Well, I wanted to. I do it for a reason because
Last time was 17.
Because I want to make sure that I'm in line with what I want to be in line with what's on the Echo Center. That's why the particular numbering is. And I left my last lecture copies upstairs, so I couldn't cheat and do what I usually do. I have no memory, so.
They all have 18 from.
All right. The consensus is that this is the 18th lecture. I'm sure there's enough wiggle room in there, one way or the other, to make sure that we're all right. Okay, so demodulation of FM, and what I'll do is I'll start by looking carefully at the form of the message signal, or rather the form of the signal that's transmitted down the channel and recognizing that what we really want out of this is our message signal. That's the goal, that what we want. And we've done a very good job of protecting it inside the cosine. Now, if we think a little bit about what this means, then we have the A will be a constant, or it should be a constant. This amplitude of our sinusoid should be a constant. So I'll just go ahead and I'll sketch, the parameters, the minus A over 2 to positive A over 2. Okay. I guess it's just minus A to A, right? Minus A to positive A. And what happens on inside of this is that the frequency changes. There's an instantaneous frequency, and the instantaneous frequency is just the derivative of this phase term in here. And that instantaneous frequency changes in accordance with M of alpha. And so sometimes it's high frequencies, sometimes it's slow frequencies, and sometimes it's medium frequencies and high frequencies again. Okay? So if I look at this, I can say, well, okay, I've got high frequencies here. I've got high frequencies, medium frequencies, and low frequencies, and medium frequencies. And this is just a schematic. It's not saying that all FM signals look this way. It's just that this is sort of what could happen for this message signal. And so one thing I can do is I can figure out, okay, what happens if I what happens if I discriminate this signal? What happens if I discriminate this signal based on frequency? In other words, what happens if I go through some sort of a filter that has a frequency response that's not flat across frequency? In other words, supposing I have an h of omega, and I have, I'll just draw it this way, in omega. And so what I have is for high frequencies, and I'll even label this, I'll say this is high frequencies, this is medium frequencies, and this is low frequencies. Okay? Same qualitative scale that I used before on my time domain plot. Okay? Now, if I take this guy here, if I take this transfer function here, and I take a look at this, and I take a look at this waveform, the high frequencies are going to see a high pass. They're going to give you a large relative amplitude on the way out. The low frequencies are going to give you a lower pass. And so maybe here I'll only see a certain pass through my filter. And then for the medium frequencies, I'll get somewhere in between. Okay? And so now what I've done is I've discriminated the parts of the signal, the instantaneous frequencies of the signal. I've discriminated them and made them into an amplitude. So let me draw this even more appropriately. I've got high frequencies, low frequencies, medium frequencies, and then high frequencies again. And if I sketch the envelope of this, and I'm a little sloppier about sketching the envelope of this, sort of rounding things off a little bit. This guy looks here like an amplitude modulated signal. This is beginning to look like an amplitude modulated signal. Has an envelope, and this envelope appears to be representative of something about M of t. And I'll even go so far as to say that this signal looks something like an amplitude modulated signal. So it's similar now to an amplitude modulated signal. What kind of a filter is this? It's a high pass. The high frequencies get passed, low frequencies get blocked. But it's quite linear, so I have to do some fooling around with the order of the filter, maybe, and I have to build it carefully. So maybe I know that I need a blocking capacitor, an AC shunt, in series with my signal, and I think I can adjust the slope by putting a resistor across it, and then make that relative to. So if I have a rough input and output, I have a high pass filter. Okay? Now, this high pass filter is also a differentiator. Right? A high pass filter is a differentiator. A low pass filter is an integrator or an averager. I've tried to go over that about 1 million times, and the reason I've tried to go over that 1 million times and to get you guys to buy into it is for exactly this moment in our lectures. Okay? Because now what I can do is I can analyze the effect of this filter on this signal here much more precisely and much more nicely. So this filter is a differentiator and so what I want to do is I want to know d psi fm of t dt. Okay? So if I differentiate this, the A stays the same, we think. It's a constant, right? I'll come back to that in a second. The integral does an interesting thing when I differentiate in the inside of it. I strip away that integral. And so I actually see that I get m of t and not the integration of m of t. And that's true for the FM case. So by differentiating, I've reached inside the cosine term. By differentiating, I've reached inside the cosine term, and I've extracted the m of t. And now this is almost exactly an envelope representation, of an AM signal. And in fact, if you look even more carefully at the role of omega c and kf, if you take the ratio of that, you've got the modulation index mu of that. Okay? So one demodulator that we can come up with is to first differentiate, which is a low-pass filter, and then use a diode bridge, or even just a single diode, as an envelope detector. Okay? Now, that's the one major thing that can go wrong with this, or what is one major thing that can go wrong with this? I'm at the receiving end. My signal has gone through some number of kilometers, maybe 100 kilometers of airspace.
Frequency shifting?
The answer is frequency shifting. What would cause a frequency shift in my atmosphere?
Change in index.
So in fact, in order to generate new frequencies, in order to shift frequencies, I need some sort of nonlinearity.
Right.
Okay. So it's not particularly likely that I'll see a nonlinearity in an atmosphere. In a fiber, like we talked about at the end of last class, yeah, your propagation medium is definitely going to have some nonlinearities in there, and therefore you can get new frequency shifts. But in this particular case of this old school FM example, the atmosphere is probably going to be linear, but what could happen to my signal? What could happen to the strength of my signal? It can weaken. And will that amount of absorption or attenuation or weakening, will that always be constant? No, there'll be all kinds of weird things that'll cause fading in and out, back reflections off of the surface, off of barns and buildings and things of that nature, will cause, in particular, well, we hope that that A is not a function of A of t. So if the channel has fading in it, if the channel has something that's going to mess up my reception as a function of time, think about an antenna that's being wiggled by the wind, very slightly changing the antenna gain, or the absorption, or the detection of that antenna. So that means that my amplitude of my overall signal is going to vary, and the math that I just did wouldn't hold. I'd have to have some term of dAdt in there, and that would look an awful lot like the message signal. So any variation in the channel on A of t is going to interfere or give you a noise term on my A. Is there a fix for that? You're a design engineer. You just implemented this. It's not quite working. Is there anything you can do to make A a constant? Let's go back to the original expression. A is small and changing at time. Any clever design ideas? Yes?
Could you just make it much larger than whatever the message would be, or it's like so big?
So the answer is make it bigger. And so what'll happen then is you have a much stronger signal. And what you're basically telling me to do is to not go 100 kilometers, but to go 5 kilometers or to go 10 kilometers. So basically just take the hit on range.
Well, or set repeaters or something.
Or set up repeaters, but again, that's still taking a hit on range because I have to put in. Any other good ideas? It's not a bad idea. It's just expensive, and you don't want to limit your range. Well, do you care about nonlinearities in the circuit that you come up with here? Think about the last class.
FM doesn't matter.
It doesn't matter. FM is pretty robust with respect to nonlinearities. In fact, it thrives on nonlinearities. That's a little strong, but not horrible. And so, is there a way that I can force A to be the final A to be a constant? You've probably done this by mistake up in the lab.
I guess if you know what the attenuation on the receiver is going to be.
You don't. You don't know what the fading is going to be. You don't know what the variation in A of t is. You're just stuck with a capital A of t coming in. What if you ran it through a limiter, like an op amp, like an amplifier that had a gain on it, and it ran out of gain because of the bias, the low bias? So that might, so then you'd bring up any little wrinkle on your envelope. You'd bring that up to a constant amount. Now there'd be distortion of your signal, but you don't necessarily care about distortion of your signal. So one idea that you might think about, and I'll put maybe, is maybe use a nonlinear element like a limiting amplifier. so that the weak signals gets boosted up to 12 volts and the strong signals get boosted up to 12 volts. And in fact, if you play with that carefully, you might even not have too much distortion. Okay? So just so, again, this interplay of solving an ideal case, looking for warts and problems, understanding the effect of those warts and problems, and then coming up with different types of solutions to those issues. Very much a part of the design process. I don't want to stand here and tell you that, oh, this will work perfectly. Okay? But I do want to give you some idea. And you have these kits, you have these tools in your toolbox. So I'm just kind of encouraging you to reach in there and play with them a little bit and see what, think of them in ways that you haven't used them before. Okay? Design philosophies. Okay? But regardless, because of this impairment, because of A is usually a function of T, and because of other things, and we know that envelope detectors are not the greatest choice, but because of all this, there are better ways of doing this. And so, one such way, and I'll finally get to introduce this circuit element, is to use a phase-locked loop. Okay? Or PLL. Okay. Now the book talked a little bit about a phase-locked loop with respect to AM, and I skipped that section, and I chose to introduce phase-locked loops in this because I think it's a more natural fit, but that's a matter of choice and taste. Now, so let me walk you through a very primitive view of a phase-locked loop and just enough math to make it look good. There have been books and books written about phase-locked loops. When you implement them digitally, they're reasonably straightforward. If you implement them in an analog setting, they can be really quite challenging. And usually they work only over a narrow range. Okay? So to give you some guidance on about all that. The fundamental piece to a phase-locked loop is an element called a voltage-controlled oscillator, or a VCO. Okay? And the input to the voltage-controlled oscillator is a voltage. The output is a sinusoid. The output is a sinusoid that depends on the voltage, whose frequency depends on the voltage. Okay? So I'll put V in here. I'll put A cosine of omega t. So the omega here is proportional to the input voltage. So I wiggle the input voltage here, and I change the frequency of my cosine. If I wiggle this input voltage quickly, I can wiggle the output quickly. That by itself would make a nice transmitter for an FM signal if you think about how to use that in that context. Here we're going to use it at the receiving end. Okay. Now just to give you an example of this, think about a crystal oscillator. In a crystal oscillator you have a little, say, a piezoelectric crystal, and you apply a voltage on that crystal, and the voltage on that crystal will change the stiffness of that piezoelectric crystal. The piezoelectric crystal will oscillate at say, the square root of K over M. The spring mass, spring constant in the mass, the square root of K over M. So if I change K or I change M, I'll change the frequency of the oscillation of that spring mass system. So if I can do that with a voltage, that's the piezoelectric effect, then I can tune this oscillation. Okay. And quartz is a nice PZT crystal, so you can make this thing fairly cheaply, and the technology's grown up impressively over the years. Okay. So by changing the voltage in, you're going to change the Q of this resonant circuit. Okay. You can do it in a different way. You can lump the PZT in as an LRC circuit, and then you'll tune the capacitor with the voltage by changing the plate distance, and that's another way of running this. Okay? But the important thing to remember from a mathematics perspective and a physics perspective is that the input voltage will give rise to a frequency, an output frequency of this oscillation. So changing V will proportionately change omega. Okay? So what we want to do in our phase lock loop is use this VCO, and I know I have an input and an output to this VCO, and I know I have a signal, like an FM signal, coming in to my system. And I'm going to write this in a simplified mathematical way. If this were an FM signal, if this were an AM signal, then the message signal would just be in this theta input term, just be proportional to this radian phase shift. If this were an FM signal, then the message signal, the integral of the message signal, would be in that theta term. Okay. So if I want to use a phase lock loop as a receiver for an angle modulated system, FM or phase modulated system, I know I have my VCO in here, and I know I have, I'm thinking I have my VCO in here, and I know I have at some point an input, which is my received signal. Okay. Now I have to think a little bit about what I want to do with this guy here, and this guy here is going to have some, it's going to be some, it's also going to be a sinusoid. And so I'm just going to draw this as 2 times some amplitude B. And I'll have a cosine term. This is Latinoing the answer a little bit. It doesn't matter because we can adjust the thetas all day long. And I'll have omega CT. And I'll have a plus theta output of T, just to contrast with the input of T. That's my message signal. That's the received signal coming in. So if my output of my VCO is of the form of a cosine of omega CT plus some time-varying phase shift, and this isn't too far off what my input is. This is a sinusoid with a carrier frequency and a time-varying theta I. Then what I want to do is somehow I want to compare the output to my VCO with my input to my system, my input to my phase lock loop. And I've got a couple different ways of doing that. I can sum them together, or I can subtract one from the other. But that doesn't seem to get me very far mathematically. A sine of omega CT plus theta I T minus or plus 2B cosine of that doesn't seem to be really conducive to some really fun trig identities, which we always know we love to use. So summations may be too linear, maybe too boring a way to compare those two. Another way, another piece another tool in our toolbox, another component that we've played with all semester is a mixer. So let's just, for fun, as an inventor or as a design engineer who's just messing around, let's stick a mixer in there. Okay? And then we'll route this guy up into there. And the output of this I'll call I of t not for current, but for intermediate signal. If I have an input and output, and this is a I for intermediate of signal. Okay. And in fact, right now, we can write down what I of t is. In fact, we might as well, because that's a nice welcome break from trying to figure out what else goes in this phase lock loop. Right? So let's see what we have. And that's equal to A times B times the sine of omega c t plus theta I times the cosine of omega c t plus theta out. I guess there's a factor of 2 in there. I guess I'll kill that. And then I'll use my trig identity. This is the sine of A cosine B. So that's going to be the sine of the differences and plus the sine of the sums of those phase angles. I'll write it down and you'll see. Sine of A cosine of B gives me a sine of A minus B. And then I have a sine plus a sine of A plus B, this guy plus this guy. And that's kind of nice because I've got a term that's at twice omega ct, and that should be a clue for what we can do with that. Okay? Yeah, we have these other time-varying functions too, but we know that this twice omega ct is a very high frequency. Okay, so we've seen that before in this class, and we have some kind of approach to doing that. This, on the other hand, is a sine of the input message signal minus the sine of the mimicked message signal. If I'm comparing this guy to this guy, presumably I want something there that gives me that's related to my message signal. And if it's equal, all the better. Okay. So I've stripped away the carrier frequency here, and I've got what is my input signal compared to what is my signal what's my signal that's being generated by the VCO. And then I've got this other high frequency term that, well, frankly, it doesn't do much for me. I've got a plus of the two phase shifts, and I've got twice the frequency. So just being real biased, what do I want to do with that? I want to do a low-pass filter to get rid of it. Block with low-pass filter. Okay? And that tells me something very real then about what to do next in my loop. Right? And so what I'll do, and I'll be a little bit general. Okay? We can say I want a low-pass filter, and we do want a low-pass filter. Okay? But the art sometimes in doing these kinds of derivations and doing these kinds of explorations, these design explorations, the art is you might as well load in a little bit of extra degrees of freedom to take care of the things like the low-pass filter that you know you want, but also to give you some wiggle room to sort of do other things that may be good or may be bad or may be neutral, but you'll find out about them. And so what we'll do is we'll put in a generalized loop filter with a response h of omega. Okay? So part of this loop filter is going to be a low-pass filter, without a doubt. Without a doubt, part of this will be a low-pass filter. And the other part of it will be flat across all frequencies, or it could come down and block DC, and it can do that at perhaps some interesting slope. Okay? Now, in a digital implementation, this loop filter is going to be realized with a high-order feed-forward filter, and you can do very, very well. You can adjust phases independently of magnitudes, and you can do that with great precision at the cost of the sampling rate, the speed of the whole system. Okay? And so from a digital perspective, you can spend a lot of time designing the perfect loop filter and implement it and realize it in a DSP really nicely. And for that reason, there's a lot of advantages to working in the digital domain to do all this stuff. If you're going to do it if you have to be at high frequencies, optics, RF, and so on, then you can't get away necessarily with a digital filter, with a DSP. It may not be cost effective the faster you go. Although, gosh, if that's not changing these days. And so, the design of this H filter in an analog setting is often the critical piece to a phase lock loop. If you make it too fast, if you make it too slow, that is, you block out too much, you make it too much of a low pass filter, you make it too slow to response, the time that it takes to feed back through this loop, and I might as well go ahead and finish the structure of the phase lock loop. If I make it too slow, the time that I go through this is the time delay that I go through all this is very, very slow. And if I want to compare this guy to this guy, and it takes an awful long time to generate this guy, well, this guy's moved on. It's different. And I'll never catch up. So if I have too strong a low pass filter, then I'll never catch up, and I'll just be chasing my tail all the time. I'll never achieve lock in my phase locked loop. Okay. If it's too fast, then I may not do a good enough job of discriminating that, or worse yet, I may have some instabilities that creep into my system. So there's a balance, and generally, if you want a rule of thumb, I don't know if you'll ever use this, but if you want a rule of thumb, you should never go higher than a second order analog filter for that, and that's very limiting. That's very limiting on the shape and the scale of that. Okay, especially if this happens to be an active filter. Okay. All right. So this is more or less the assignment, or this is more or less the layout. And I've done just a slight bit better than just laying out the blocks. I've tried to argue why you would actually come up with these elements. The only thing I kind of cheated on was to let you know that there's not much else needed. Okay? Which probably you guys are a little bit relieved, because that makes the analysis a little bit faster. That's a joke. The class is cracking up. I'll just record that for the record. Now take a look at this error output. Okay? This error output is what's feeding the VCO, and it's telling the VCO, this is the kind of sinusoid I want. And what I really want is that this sinusoid match up this sinusoid. So what I really want is I want a nice comparison between the input phase as a function of time and the output phase as a function of time, and that's entirely controlled by this error signal. So this error signal, in fact, is representative of my message signal, theta I of t. Okay? So getting this working is our next job. is to show that E out is enough. And so E output of T E output of T here is, okay, I'll write this as H of T in the time domain. If I have my input I of T into my loop filter, and my output of my loop filter is E out of T, and I've just said this is a loop filter, I'm suggesting that it's linear time invariant, and so the output E out of T is the convolution of I of T and H of T. Or it's I of omega multiplied by H of omega if I want E out of omega. Okay? But what I really want is the progression in time of what's going on with my message signal. And so I can write that convolution integral as here's my H of T, convoluted with my input signal, and my input signal, I of T, is equal to A over B, AB over 2, times the difference, sine of the difference between the phases. Or in terms of a convolution integral, my dummy variable is x instead of tau. Notice that I have to figure out a way to start this. It's possible to build a perfectly good phase lock loop and never have it converge into a lock because you start too far away. Okay? And that's part of the issue there. This guy here is the theta of the error signal. I'll call that theta of the error signal. Okay, put that aside for just a second. Now, the output of the VCO, the frequency that's generated by the free VCO, is going to be the instantaneous frequency of this signal here. Okay? The frequency that comes out of the VCO is going to be the instantaneous frequency of that guy there. The instantaneous frequency of that guy there is found by taking the derivative of all the stuff that's inside the brackets of that cosine term. Do the differentiation, and I get an omega c plus theta output, and I'll label the time derivative as a dot. Hopefully you've seen that enough times that you're comfortable with it. I know you've seen it before. I hope you've seen it enough times that you're comfortable with that notation. So that's the time derivative there. That's the instantaneous frequency. And that's proportional to whatever voltage I put on the VCO. It's proportional to whatever voltage I put on the VCO. So I'm going to multiply my voltage that I put on my VCO. That's this error voltage, the output of my loop filter. And all this is my funny notation for a constant, a multiplicative constant, a scaling constant. Okay? Don't worry. In other words, I'm getting really sloppy with my mathematics, and so don't worry about these constants of proportionality. Okay? Let me ignore the DC part of this expression. One way to say that is that I want to look at the small frequency components only. But usually I can always strip away a bias like that, or add a bias to it. Okay? My mathematics is leaving my block diagram a little bit. I have to figure out a way to ignore that, but I want to ignore it. And so now, if I go back to this guy here, I can write theta output dot of t is equal to some new constant Okay, so I can write now an expression for this output theta dot in terms of this convolution integral. If I happen to be doing an FM case, not a PM case, but an FM case, then this theta term here, this base term here, is proportional to the integral of the message signal. I know that theta error is equal to theta input minus theta output. So if I now substitute in, I can get, when I have a perfect lock, when I have a perfect lock, I can find out that my voltage that I feed onto my phase lock loop, my voltage control oscillator, is equal to the time derivative of that phase function, which is proportional to my message signal. Okay? So when everything is locked together, when everything balances out, then the phase lock loop is an FM demodulator. And a very, very good one at that. Because its whole job is to replicate exactly the input coming in. So now think about it. This guy comes in after many, many hundreds of kilometers. It's limping in. It's tired. It's been abused by the airwaves. And I have a beautiful VCO that if I give it the right instruction, I generate a signal that's close to it. I mix with it. So now this weak signal sees the strength of this signal here. So the strength of the I of t is independent. The strength of the I of t is driven by the product of the weak signal and the strong signal. If this is 10 times weaker, I make this 10 times stronger, up to a point, up to a limit. And so I of t, this mixing and this regeneration here work brilliantly to give you an I of t that's robust, even if this guy is weak. And then the rest of it, I do a little bit of filtering and I feed back, and my E out of t through all the mathematics, through the math that I just showed you, the E out of t readjusts to keep this getting this closer and closer into lock. And then once this wiggles around, this just rides around, and this output here is representative of M of t. Okay? So it's a brilliantly magic circuit. I really haven't even begun to give it justice. But it gives you the rough argument, the linearized argument for how this it behaves as a very, very good demodulator for angle modulated systems. Okay? All right. Okay. That's pretty much all I want to say about FM. So we finished chapter 5. Okay. And now we'll go on to, we have a few minutes, so I'll start to introduce, I won't get into too much of this, but I'll start to get into chapter 6 and so on, which is a digital approach. And now, if I can ask a really unfair question, it's unfair because we've never talked about this before, and in fact it requires a concept that we've never even talked about before. Why is digital preferred in so many of our systems to analog? What's magic about the digital domain? It's easier to deal with. That's true.
Smaller packages.
Smaller packages, yes?
Ideal environments and immune to...
Ideal environments and immune to, and I'm waiting for the magic word there. Impairments such as?
It's robust to noise.
It's robust to noise. Why? And that's why it was a very unfair question, because as we go into this last bit of the class, noise is going to be more important. So why is it robust to noise?
Because there's only a finite number of outputs.
Let's say there's only a finite number of outputs. I'll help you out. There's 2 of them. In the simplest case, not all digital, but in the simplest case, there's a 0 and a 1. So go on.
So if there's noise, I mean, you can have a delta, like if it's 0.7, you can say it's 1, you can just round up or down.
So you can threshold, and the suggestion was 0.7 can be rounded up to a 1, and then it becomes a real 1 once you round that up. And I may have given this analogy before. I'll give it again. In the old days, we had Xerox machines or photocopying machines, but we didn't have all the digital. We didn't have digital printers or anything like that in the way old days. And so, if you wanted to make a copy of a piece of paper, you'd put it down on the copier, and you would photocopy it, and out would come a magic copy of what you put in, complete with some noise on it. Some stray dust would cause extra little dark spots, and the lights and the print would fade in different manners. And so then I would give this copy out, and my colleague would want a copy of that copy. I kept this well away from him, but then he would go to the photocopy machine and he would photocopy it, and the dark would weaken even more, and there'd be more dust spots on it. So there'd be the noise on that would propagate, copy after copy after copy after copy. The noise, you could argue, would just add. Your signal would degrade, and your noise would add, and after a certain number of copies, you were really out of luck. You could barely read it. Contrast that with the digital age, where we have a PDF file, for example, and every time I want a new copy, I print from that master copy that has all the ones restored. So the first print has a degraded signal-to-noise ratio, but not by much. And then every one afterwards is restored. Okay? And so that's exactly the case. That's exactly the case in communications. And in fact, what I just suggested was an example of a communication system, a weird one, where I replicated my message signal again and again and again through a noisy process. Not unlike, say, a fiber optic system today, which starts in Dallas, goes to Chicago. It's about 1,000 kilometers or so, maybe a touch less than that. Every 100 kilometers along that way, maybe it's more than that, about 1,600 kilometers or so on. Every 100 kilometers along the way, my signal would drop 2 orders of magnitude, but then I would see an amplifier and it would raise up 2 orders of magnitude. It would propagate another 100 kilometers, in which case it degrades 2 orders of magnitude, and then bounces up again. It'll make it to Chicago fine after 16 of those. Attenuation, amplification. But in that analog process, every time I amplify not only the signal, but I also amplify the noise. So on every one of those stages, on every one of those spans of my network, of my system, I have an increase in my signal to noise. In the old days, ironically, I would have a receiver every 100 kilometers. I would receive, I would completely regenerate my signal, and I would send out a fresh one on the output every 100 kilometers. And that was a perfect digital restoration of a noisy one coming in. You might ask, why did the optics folks take a step backwards from digital to analog? And the answer is the cost of that digital regen was so high when you multiplied it by the large number of wavelengths. It was cheaper, it turned out to be cheaper to take the hit on noise and then work really hard to control your noise. And so you could go further and further and further. Now regens are done after, say, 3,000 to 6,000 kilometers. And in some links, say across the Pacific, 9,000 kilometers. Okay? But that's the point to running with digital. That's one point to running with digital. There's others as well. You mentioned that it was easier to deal with. And I'll interpret that as saying you can do a lot more interesting algorithms, and not just process not just filter or restore your signals, but filter them, process them, sort them, organize them, and do things encode them and do things in much more flexible manner to take into account idiosyncrasies. Okay. All right. So let me draw the transmitter block diagram. And there are 3 blocks. And my lectures will just cover each one of these blocks successively. The signal is sampled. It's quantized. And then it's encoded. And then it's sent down the channel. And the input to this is my message signal. Okay. On the receiving end, I'll have some kind of receiver, a detector, and then a decoder. And then typically a low-pass filter can be used to reconstruct, and out comes some approximation of M of t. So this is at the receiver. And the organization of the next couple of lectures are going to be to talk about sampling, talk about quantizing, and then talk a little bit about encoding. A couple of things to bear in mind. The input signal is analog. When we sample it, we sample that analog signal probably at a certain constant rate. So we only have discrete samples. The height of those samples can be anything. The height of the samples can be anything. And so for that reason, what's here will be a discrete time signal. It's not digital yet. It won't be digital yet, because you're only sampling at certain instances of time, so you have discrete time, but your amplitude can be anything it wants, so it's continuous amplitude. Then what you do is you bin it. All the voltages between this range and this range are the same, and assigned a digital code. 11101 will handle all the voltages between 1.7 and 1.83. A bizarre, weird example. At that point, you have a digital signal. Okay. Now I'll say something that's going to be confusing, and I sometimes think I'm going to be just too clever by half to make it this confusing. What goes on the channel, obviously, is the digital signal. So that 11101 is going to be sent down the channel. Right? But the channel is fundamentally an analog component. And so it doesn't know what a 11101 is. It knows what 5 volts, 5 volts, 5 volts, 0 volts, 5 volts is. So what's sent down the channel, and this is probably the job of the encoder, or probably a good description of the job of the encoder, is an analog representation of the digital signal. Okay? So when I talk about encoding, the magic of encoding is to shape those ones and zeros into something that's really advantageous for the particular channel and the particular application that you have. If we go back to my photocopy example, there's actually a lot of work that goes into the precise shape of the pixels of ink on the page. So we look at it and we just see a dark spot, but in fact the shape of that spot is actually fairly carefully engineered. It's not perfect, but there's a lot of engineering that goes into the microscopic shape and application of the ink. In this process, what might be better than that process to give you a final resolution or a final image that looks nicer. Okay? So in that case, the encoding is the precise distribution of the ink of a spot of a pixel on a piece of paper. The projector displays, the DLP projector displays, they had two applications in the early days of that MEMS device. One of them took off, and that's the printer. That's the projector displays. The other one, and I worked a little bit on the optics in that. And then the other one I also worked on, but not as much, was the printing application. So you would use for example, the image of the light to say burn, or to expose a negative, or a chromophore of an ink. And again, the optics of that were nice, so that you could actually tune the shape of that pixel to get much sharper, much nicer images, or much faster images. Two different regimes. Okay? Didn't take off, and one of the reasons for that was the shape of the silicon for the projector displays used the die of the silicon wafer very well, whereas for the printer it was long and narrow for a desirable print, and you couldn't get very many out of a wafer. So the fundamental economics of the size of the device and the size of what you're making it out of drove one application out of the market. Interesting. Okay. All right. I think this is a good place to quit. Next time, what we'll do is we'll talk a lot about sampling. Probably get a little bit into quantization. Time after that, we'll talk about quantization and maybe get into encoding. Time after that, we have our exam. And then the time after that, we'll finish up encoding. And we'll do our first example of noise. And then when we come back, we'll talk some more about noise, and in fact noise in AM systems and FM systems. And that should take us pretty much to the end of the month and the end of the course. Okay?